Hello everyone. We are group 13 today. We will show our demonstration of Lab 4 of EE533. And these are my members of our group. And this is our information about our group members. Okay. Let's move next. My name is Yijun Qiao, and I was responsible for the part 4 and part 1 to part 4, and the Yanchen Zhang will responsible for the part 4, part 5, and part 6, and the Mindy Luo will responsible for the part 7. And then I will start my part. My part is from part 1 to part 4, and these parts cover the complete preparation process before implementing and test our own hardware design on the net FPGA board. And I will discuss how we set up a net FPGA virtual machine environment to generate FPGA bit fields and configure US VPN for remote access and finally configure the net FPGA working environment like including the SSH and the terminal management. Okay. Let's move to the first part. First part is about downloading and setting up the NetFPGA tool virtual machines. And the purpose of part 1 is to create a stable and stabilized development environment for NetFPGA. There's no need for us to install all the required tools manually on our local machines. And we use a pre-configured virtual machines provided by the official NetFPGA. First, we downloaded the foreign virtual machine images on our format, and then after the virtual machines both successfully, we open terminals and switching to the root users. Like that, we should type the SU and type up their password, and after that. Once we logged at our root, we navigate to the NetFPGA project dictionary located at the root NetFPGA projects. And in this dictionary, we copy the reference root project and rename it as Lab4. This reference design serves as a base template for our experiment. After copying the project, we move into the synthesis dictionary and run the make command. Because there's a make field in a base dictionary that provided by the official NetFPGA, and this command will create the bit field. And during this step, I think it's very important to monitor the terminal output to ensure that there's no errors occurred, and such as synthesis failure or mapping errors, they must be resolved before the continuity. Okay. Firstly, I will show you the result of the first step 1. First, we should open the virtual machines. And you know, these steps will cost a lot of time, so we just show the result. No, before we use this virtual machine, there's no file named as Lab4 in the reference dictionary. So we can just open the computer systems, open the row dictionary. Where's the row dictionary? Here. Sorry, row dictionary, NetFPGA projects, and you can see the Lab4. Yeah, you can see the Lab4. We have the Lab4 dictionary, and in the synthesis, we will go to the NetFPGA bit fields. Okay. Okay, let's move to the next step, part 2. For part 2, before we start part 2, we should do other things to to make preparations, because the goal of part 2 is to integrate our own Verilog design into the NetFPGA project and generate custom bit films. And in our case, this includes hardware modules such as many IDS logic designed in our earlier labs. And firstly, we should take the Verilog fields, our Verilog fields, and any IP core films generated from the schematic to Verilog conversion, and place them into the appropriate project dictionaries. Typically, Verilog source fields are placed into the source dictionary. We'll include a software-related field go into the include and SW dictionaries directions. In the source dictionary that not already exists, so we should manually recreate it. It is important that all the required modules are included and that the top level modules matches NetFPGA project interface. So firstly, the very important thing is to move our Verilog fields to the virtual machine. So we choose the method to create the shared films, and in our local desktops, we created the fields named the shared fields, and I moved all the needed Verilog Verilog documents into the source document, and this is all the needed Verilog fields. And then I moved it. Then I moved it to the to my virtual machines. You can see intermediate. Here's the name of the file with the shared files, and then I can copy all the needed all I needed Verilog film to my own dictionaries. You can see this was my this is my own dictionaries. Where's Lab4? Sorry. Okay, first we should root NetFPGA projects and Lab4. You can see I can just copy all the Verilog film into this source document, and you can see that is all needed in these films. And next and next, if the compilation after the copying all the necessary fields, and we refer to the synthesis dictionary and run the make command again, and this process recompiles the entire device and node, including our custom logics. And if your compilation completes successful, a new bit file is generated, and this bit file represents our custom hardware design and will later for download to the NetFPGA board. And it is the same method. We just use the make command to use the make field in the synthesis document, and then we will get our own bit films. And I will show you. NFPG project Lab4 sources. Back synthesis, and you will get the top project here. Okay. For the part 3 focus on the configuring the USB VPN, which is required to access the NetFPGA service remotely. When working outside the campus network, VPN access is mandatory. You can see that I have connected to the US VPN, so I can move to the next step. The next step is about the NetFPGA environment configuration and SSH environment. Firstly, we ensure that open SSH detects the errors such as the nano and installed our local Linux machines, and then added the SSH client configuration field located at the elect SSH as the configure. And in the fields, we add a specific setting to allow order key exchange and host key algorithms. This is necessary because some NetFPGA services use legends SSH configurations. And next we download the operating script provided in the lab. To support this script, we install the normal terminals and the script with our term numbers and team pro password. This opens several terminal windows, each connected to a different node. Inside the remote environment variables such as N0, N1, N2, and N3 storing the IP address of the different nodes, and these variables are later used for testing connectivity and performance. And I will show you the result in a step. Firstly, we should open the terminal and change it to the sorry. Yeah. And next, we should connect to the FPGA from a remote connection. Here you can see we have connected the FPGA board successfully. And then we should do some experimentations. Like first of all, okay. And then check it. Yes. 2 and 3. Yes, that is correct. And about that, we can, we can play in the any node of this from N0 to N3, and then try it again. We can just take this and try other. For example, or we can tie in node 0. Sorry, node 0. Yes, and then we can ping. Let's find this IP address here. Like that. Okay, you can see they have makes a connection between the node 0 to node 3. That's it is okay. This is a part 1 to part 4.
Hello, this is Yanquan, and my partner Yijun has, uh, just demonstrated the reachability of each node. And next, I will introduce our groups, lab steps 5 and 6. So first, let's look at these 4 task scripts. NIC soft, it is for the testing the data forwarding performance under the TCP protocol after an IC is programmed into the FPGA, and NIC stress, it is also for the testing after the NIC programmed into the FPGA, but its test is a UDP protocol, and test is it is a small package stress test. And the router soft and router stress, they are the test scripts for router version. It is for the FPGA is used as a router. And now I will demonstrate how to conduct these tests. Firstly, let's run the open term to connect to the FPGA and 4 nodes. Now we have successfully connected to the nodes and FPGA. So in the step 5, we should run just one test. It's for an IC and under the TCP protocol. First, let's kill the RKD process. And to to program the sorry, let's find the file firstly. And now the FPGA should work as an NIC. And let's run the NIC soft. The test script will summarize the data forwarding performance of different node pairs into a report named TCP NIC summary. And we can see this. The log file has been created and waiting for the test finished. Now we can see all the node pairs has nearly 90 MB/second megabytes. And now the step 5 has been completed. Next, I will demonstrate the 3 tests in step 6. Although the first test in step 6 involved a TCP test of the router, but to avoid repeatedly program the NIC and router bit file onto the FPGA, I will first perform the UDP small package stress test on the NIC, which is a second test of step 6. So we don't need to change the FPGA, we just need to run another test script. It's NIC stress. And we can see the log file is here, waiting for it finished. You can see the content of it. And during its running, we can process for the next step. Enough. Reference router. Wait, okay. Row 3. It is the last row, so it will be down soon. Okay, let's check the summary. You can see it has 20 MB-second bandwidth and 90% loss possibility. It's so high. And now let's run the router test. So firstly, let's program the router bit file into the FPGA. Okay, and also create a RKD process background, running background. Okay, we can see the RKD process has been created successfully, and now the FPGA will work as a router. Router stops. It test is down to the router for the TCP test. Well, it has a much more bigger bandwidth. So from the last apps, the router stress. Let's see the difference between NIC and router. You can see the router is better. It works. Yeah, it works better. The bandwidth is bigger, and transfer is bigger. Now waiting for the UDP test result. We can see I predict the loss possibility might be lower and bandwidth might be bigger. Let's see. Okay, now we can see the loss possibility and bandwidth all becomes better when the FPGA is working as a router. And next, my partner Mingy will demonstrate the step 7.
Okay, so in this part, I'm going to introduce part 7, which is implementing the router with many ideas on our NetFPGA board. We mainly made the modifications in IDS.v, IDS.xml, and IDS-reg. So the first step requires us to implement the pass-through version of IDS onto the NetFPGA board, which simply connects input directly with output with a wire type variable. This step is not shown right here because our complete version of IDS can be directly implemented on the board. So let's now take a look at the modifications made in IDS.v. Okay, so we implement a logic analyzer right here. The logic analyzer is made up of a block RAM. It can capture and replay the state of data packets during the processing and verifying whether the pattern matching and packet dropping logic is functionally properly. So its core function is right here. Its core function is to capture the data at two critical nodes of the data path. One is before the data enters the packet dropping FIFO, which uses the signal in FIFO mem, and the other is the data output, which is called the out FIFO mem. So each capture point is equipped with a 256 depth memory, with each entry storing 72 bits of data, which includes 8 bits of control signal and 64 bits of data. The right pointer uses a saturation continuing method, incrementing from 0 to 255 and then stopping. The software can access the captured entries by setting the read pointer, and the 72-bit data readout is split into three 32-bit registers for the software to read, which is the code right here. So these are all the added logic parts of the logic analyzer. It's very simple. It just captures the data in registers and gives an access to readout. Yeah, so that is all of this part. So, okay. After making modifications in IDS.v, we have to modify IDS.xml, which is here. Because all the input and output registers are declared in this part, we have to declare all the register used. So we have to add the register used in the logic analyzer into this file. Okay, as you can see right here, this is the part that we added. And I think no modifications is made in the project.xml. Okay, so let's move on to the last part of modification. That is IDS-reg. This part serves as a software interface between the user and the IDS hardware module based on Perl. So this script reads and writes the memory mapped registers on the NetFPGA platform by calling the system commands regread and regwrite, enabling configuration, monitoring, and debugging functions for the IDS module. This script mainly provides 6 main commands, which is right here. Okay, so the reset command resets the match counter by writing 1 to the control register and then comes back to a value to 0. and the pattern command receives an ASCII string up to 7 bytes and converts it to a 62-bit matching pattern and an 8-bit mask. Then write these to the pattern high and pattern low registers for the hardware matcher to use. And the equal matches command reads and displays the current match count, indicating the number of data packets that have been detected and discarded. And the allReg command reads and displays the current values of all the related registers at once. The LA dump in and the LA dump out commands are used to dump the data captured by the logic analyzer. So all the functions are fulfilled here. And after the user specifies the start and end indices, the script sequentially sets the read pointer and reads the corresponding 72-bit captured data, which is split into 3 32-bit registers I've just told you just now, and outputs the control field and the data field in a formatted manner. Okay. So all the modifications are made, and the next step is to make the bit file and implement it on the NetFPGA board. So we use make command, then SCCP it onto the board, and use nfdownload to implement the bit file. So I've already SCP the bit file onto the NetFPGA board. So let's now nfdownload it to implement it. Okay, so the nfdownload is good. Okay, so the next step is to run the IDS reg. We first reset it and set the pattern as ABCDEFG. And then we check the values of all registers by using the allReg command. So let's see. Okay, so it's good. So the next step is to verify the functionalities. So let's first build some RKD to keep it connected between the nodes. Okay, so let's ping them between different nodes to see whether it is connected. Okay, it's good. So next, we are gonna set one server and 3 clients to test whether the IDS is working on TCP mode and UDP mode. So now let's set the node 0 as the server and node 1 to node 3 as the client. We are going to set by using iperf-s and iperf-c command under TCP and UDP. And we assume that node 1 and node 2 are sending good packets, while node 3 is sending bad packets, which includes the pattern ABCDEFG. And one thing to note that while using iperf-c, we are sending packets from client to server. And since iperf command cannot directly assign specific payload to the packet, so we use iperf -F to send a file serving as the payload. So now we are testing TCP because we don't add -u to the command. According to the working mode of IDS for TCP, the ideal outcome should be that node 0 should be able to establish connections with all 3 nodes, but it can only receive good packets from node 1 and node 2, but not the bad packets from node 3. Okay, let's see. Okay, so as you can see, these 2 nodes which are sending the good packets are connected with the server, and it has a bandwidth indicating that the file is transported successfully. While this node which sends the bad packet right here, it establishes a connection with the server, but it don't has any bandwidth, so it indicates that the bad packet is dealt by the IDS, and it is dropped, so it don't have any bandwidth. Okay, so the results of TCP is good. And now let's check the matches register to see whether it increments or not. Okay, as you can see, it has a value right here. So the TCP is good. So next we are gonna test the UDP. It is nearly totally the same as TCP. But since UDP is a connectionless transmission protocol, it does not establish any connections between 2 nodes. Therefore, the ideal outcome should be that node 0 can only receive good packets from node 1 and node 2, but not the bad packets from node 3. And it don't establish any connections here. So okay, now let's see the results. And for the UDP node, we are gonna add -u right here, so we can shift to the UDP node mode. Okay, as you can see, these two nodes are sending the packets successfully, and this node still cannot send the bad packets. So yeah, as you can see right here, the results are good. So now let's check the register again. Yeah, it increments again. So the UDP mode is also good. Okay, so the overall function of the IDS is good on both TCP mode and UDP mode. And okay, so that's all for this part, and thanks for watching.